in the current. And you can use this result to then write down an expression for, I think I erased it, for energy, magnetic energy stored in the capacitor. And actually this came from there. I erased what I had over here, but we ended up with this expression. Now, can we show that the magnetic energy, let's say we did the expression for the, we calculated the inductance of a solenoid, right? We said, what was it? It was mu naught, I think it was an N squared, an A, and an L, I think is what was in there.
Yep.
I don't memorize those things, but I vaguely remember that that's what I wrote down.
That's what you wrote.
So, what if we apply this equation to a solenoid with current in it? So suppose you have a solenoid, right, with N turns per unit length. So if this is 1 meter of length, there will be N turns, little n turns, and the current in it is I. So I. So let's say it produces a magnetic field to the right. And the area of each one of these loops is A, and the total length of it is L, lowercase l, not to be confused, right? So notice that if I apply this equation, this formula for the total energy in the inductor, what will I get? Let's see what we get. Let's play with this. That's the total energy, right? That will be 1/2 times the inductance, which is this. So I'm going to write mu naught N squared AL times the current squared. But what is the current? What is the relationship between the current in the solenoid and the magnetic field? We said that the magnetic field in a solenoid is mu naught N I, correct? So the current is B over mu naught N. I have to make some room for myself over here, so I'll have to erase this. So what I did was this. I took this expression and I plugged it in here. And I'm going to take this expression for the current and I'm going to plug it in here. So that gets squared. So this will be B over mu naught N. So what do we get? Well, I'll continue here. And this is the total energy. We get 1/2. Notice I have a mu naught and I have a mu naught squared in the denominator and a mu naught in the numerator. So I was going to give you a mu naught downstairs, right? I have an A, I have an L, right? I have N squared and also in the numerator, and I have N squared in the denominator. So this cancels that. And then I have B squared. But what is this? What is the area of one of these loops multiplied by this length?
Volume.
That's the volume inside the solenoid, right? That's the volume of the solenoid. So therefore, this expression for the total magnetic energy can be written as 1/2 1 over 2 mu naught B squared times, the volume of the solenoid. And if I divide by that, because this volume is A times L, if I divide by that, then I get the total magnetic energy per unit volume. That would be B squared over 2 mu naught. And this is oftentimes written as lowercase b. This is called the magnetic energy, and because it is per unit volume, it's the magnetic energy density. This one here is the total electrical energy per unit volume. So this one is called electric energy per unit volume. So density. That's what it's called.
Did you say lowercase? Did you mean to write lowercase b over there?
What's that?
Did you mean to write lowercase b?
Yeah, this is a lowercase b, u, and a capital U.
Oh.
I'm sorry, I should probably put a little wiggle like that. I make this one more like that. So this is like total. Here, this is total. It's a capital U, but this is usually like, maybe I'll put a little wiggle. It's a lowercase. I mean, the big thing to remember here is this. The magnetic flux, that's from chapter 29. If you know chapter 29, then it'll be easy to plug that in, right? And then this is going to depend on the current. The currents will cancel, and then you easily obtain the inductance. You'll see when you get there. All right, this is what I just did for the specific case of the solenoid, and that's the energy per unit volume. So I wrote the energy stored in the magnetic field in the case of the inductor with current I in it. Right. You can say that the energy is stored in the magnetic field, and over here for the capacitor, the energy is stored in the electric field. Mutual inductance, it's, what is mutual inductance? I actually like to start the discussion with mutual inductance, but I forgot to start it. With it, I went straight to self-inductance. So mutual inductance says the following. There's a result that's interesting that comes out of that. Let me erase this. By the way, you have lab tonight, right? But I think some of you are not going to be there tonight because you have the awards ceremony. How many of you are in that boat? I guess they left already. How many do you know? Well, we know of her. Anyone else? Are you going there tonight also?
Yeah.
Okay, so that's 2. That's it? So, as far as making up that lab,
I mean, I was in the lab.
oh, then it doesn't, then you're not affected by it. Okay, it's just for those people who have lab tonight. So, okay, I'll work something out with her so she can make up that lab. But I thought that there might be more people, so. Well, that have the lab tonight and are going to the ceremony. Maybe, like some of you are going to the ceremony, but you already had the lab, so that it doesn't affect you. So, what if you have a loop over here? Let's say this is loop number 1, with current in it, I1. So what is that loop going to generate? It's going to generate, the current in that loop is going to generate the magnetic field, right? And maybe you generate the magnetic field like this, right? It's going to go like this. Yes? Now, what if near this loop is another loop? Maybe here's another loop. Maybe this is loop number 2. Right? And what will happen is that some of the magnetic field generated by this current, I1, in this loop, some of these magnetic field lines, let's call it B1, will go through that loop. So therefore, like this one is going to go in like this, and it's going to go like that, and this one is going to go like that. So this is B1. Right? So therefore, there is going to be a flux through this loop. But the flux through that loop, I'm going to call it phi 2. The flux through loop number 2. Yes. So you can, if you like, in call the area of this A2. So the magnetic flux through this loop over here will be proportional to this magnetic field B1. Right? The greater this magnetic field produced by this current in this other loop, the greater is going to be the magnetic flux through this loop number 2. Yes? So the magnetic flux through this loop will be proportional to this magnetic field. But what's producing this magnetic field is this current I1. So B1 is proportional to I1. So, but B1 is proportional to I1. So the connection between the current in loop number 1 and the magnetic flux in loop number 2, what is that constant of proportionality? Oops. That's called the inductance, like for both of them. It's called the mutual inductance. So the symbol that's used is a capital M. So this is like, when I first presented this proportionality issue, it was just only one loop, right? There was not another loop. So we said, if there is a current in this loop, it produces a magnetic field that goes through the loop itself. And so there is a magnetic flux through the loop itself. So there is a proportionality constant between the magnetic flux through this loop and the current in the loop, and that proportionality constant is the self-inductance L. Well, here we have one loop with current in it, which produces its magnetic field, but some of the magnetic field may go through another loop that's nearby. So there will be a magnetic flux through this loop, which is proportional to the magnetic field that goes through it. But that magnetic field is produced by the current over here. So you could claim that the magnetic flux through this loop is proportional to this current in this first loop. And that constant of proportionality is called the mutual inductance. It's an inductance. It's a purely geometrical quantity, but it is an inductance that involves both loops, the geometry of both loops. In the other case, it was just the geometry of the only loop that was in the problem, which is called a self-inductance, right? But it's just inductance, right? So it's just called mutual inductance. Right? So like phi 2 equals phi m1. And notice, if, right? What happens if this current changes in this loop? If the current in this loop changes, then this magnetic field B1 is going to change. And if that magnetic field B1 changes, the flux through this loop is going to change. And what happens if the flux through this loop changes? Then there's going to be an induced voltage, an EMF, induced in this one. And in that case, the EMF is just induced, is going to be the derivative of that magnetic flux with respect to time. The minus sign is just put in there to show you that it will oppose the change in that flux, right? And then you can just say that this is minus M dI1 dt. Actually, this mutual inductance should really be called 1-2, because it depends on both of them, to remind us that it doesn't depend on just loop 1 or loop number 2, but both of them. So maybe a notation like 1-2 is more appropriate. But the book, they just call it capital M. I guess, you say it, it's supposed to be understood that it is the word mutual means that it depends on both of them. But maybe we should be reminded that it's really for both of them. Now, the interesting result over here is this. There's an interesting result over here, right? What if I run a current of 5 amps over here? Suppose I run a current of 5 amps. And I ask you, what's the flux through this loop? And whatever the shape of this loop is, right? It doesn't have to be a circle, it could be just something weird like that, right? And here we have another loop in the vicinity of this one, and it has another weird shape, right? And I ask you what is the magnetic flux through that one. And suppose that you calculate the magnetic flux through this loop. And what are the units of magnetic flux? Anyone remember the unit of magnetic flux? Okay, so magnetic flux is a magnetic field times an area. So it'd be Tesla meter squared. Tesla meter squared, magnetic flux. Yes? But this is also called a Weber. I don't know if it's 1B or 2Bs. But let's say this is 15 Webers. I don't know if it's B or something like that. So let's say 15 Webers, right? So that means that the mutual inductance is what? If this current here is 5 amps, what will be the mutual inductance of these two loops? 3, correct. In whatever units, right? It'll be 3. Because this flux over here, right? I can write phi 2 as the mutual inductance times I1, but if this is 15 and I1 is, I made it 5, then M has to be 3. Right? Okay. Now, the key thing is this. What if I now establish a current in this loop that has a different shape, another current here, and suppose I make that current equal to 5 amps, the same as this current, and I ask you what will be the magnetic flux of the magnetic field produced by that current in that loop through this one. It's a different area than that one. The magnetic field, is generated by some current in this weird loop over here. And if I ask what's the magnetic flux through this one, the answer is going to be the same as this. You have to think about that in order for you to be surprised by that, or not surprised, like wow.
I'm sorry, could you repeat that real quick?
Okay, so this is a weird shape of a loop. I don't care what shape it has. And suppose the current in it is 5 amps. And it produces a magnetic field, whatever it is, it'll be different at different locations, right? Different directions, so it'll loop around, blah, blah, blah. Some of the magnetic field is going to go through this loop, which has a weird shape. Whatever. And I ask you, and suppose that the magnetic flux through this happens to be 15. And so, 5 amps over here generates or gives rise to a magnetic flux over there of 15 Webers. So, that tells me that the mutual inductance is, what do I have to multiply this current by to get 15? 3. So the mutual inductance is 3. But it's something that has to do with both of them. So that means that if I establish a current over here, and I don't care which way, right? That's 5 amps, because the mutual inductance between them is 3. Whatever this 5 amp is, I'm going to get a magnetic flux over here of 15 Webers. Even though it's weird and it's going to have to go through it and so on, but it'll be the same flux. And the way that I showed it over here is like this, right? You can say, well, the mutual inductance is for both of them, so M equals M. So for this M, I can write the mutual inductance as the flux through loop number 2 divided by the current in loop number 1. Or I can write it as the flux through loop number 1 when the current I2 is in this other loop. But if the two currents are the same, which is what I did over here, 5 amps and 5 amps, if this is the same as that, they cancel, and then the magnetic fluxes are going to be the same, regardless of the weird shapes that they have, and regardless of how you orient them, right? So it's
So it doesn't depend on the direction of the magnetic field.
No, the flux will be either this way or that way. I mean, the magnetic field going through it, right? The magnetic flux is just, you know, so many Webers. Could be a magnetic field, yeah. So, I mean, the type of question that you can answer where you use this knowledge is something like this.